Hi everyone, we're very glad to present our RegMiner work to automatically construct the regression dataset from the code evolution history. This is a joint work from Fudan University, National University of Singapore, Shanghai Jiao Tong University, and Peking University. Bug dataset are important infrastructure for software engineering research tasks, such as software testing, debugging, and repair. The SE and PR communities have proposed many bug datasets. Nowadays, the Fix4J is the most popular dataset. For each bug in a bug dataset, it is manifested by a buggy version, a fixed version, and at least one test cases, fitting the buggy version and passing the fixed version. During software development process, a regression bug can often happen, which makes a working function fail. A regression bug is different from a general bug in that there's a working version happening before the buggy version. Therefore, a regression bug is manifested with a fixed version, a buggy version, a working version, and a test case passing the fixed and working version and failing the buggy version. In the problem setting of a general bug, we want to derive the fixed version based on the buggy version. In contrast, in the problem setting of a regression bug, we want to derive the fixed version based on the buggy version and the working version. We can see that the problem setting of a regression bug embodies a much stronger specification for us to localize and fix a bug in an automated way. While the regression bugs are common, they're hard to collect, which has a negative impact on the regression research in the community. We investigated regression analysis work from the year of 1999 and 2021. We find that the number of regression bugs used in experiments is very small. Even worse, different techniques are using different regression bugs, which makes us very hard to compare these techniques. In this work, we propose RegMiner to collect regression bugs from the code repository in a fully automated way. We consider the regression mining problem as the information retrieval problem on the code commit history. Specifically, we found a test case in the project which can pass one commit as a regression-fixing commit, fail in one commit before as a regression-introducing commit, and pass one commit even before as a working commit. Our solution consists of 3 steps. First, we search for a commit where one of the test cases can pass this commit and fail the commit before. If such a commit exists, we believe the commit is a bug-fixing commit. While bug-fixing commit is relatively easy to locate, it is non-trivial to estimate how likely the bug-fixing commit is also a regression-fixing commit. We will introduce our estimation technique later. Assuming that we find a bug-fixing commit with good regression potential, we next proceed to search in the commit history for a previous commit where test cases can pass. To this end, we need to migrate the test case to the previous commits. Here, the technical challenges lies in how do we smoothly migrate the test case and its dependencies to every commit so that we can minimize the compilation errors. Also, migrating the test case along the whole commit history is prohibitively expensive. Therefore, we need to further design an algorithm to investigate as few commits as possible so that we can find the regression-introducing commits as soon as possible. Also, the search algorithms need to deal with the commits which cannot be compiled. Next, we introduce how do we address those above challenges. Our rationale to estimate the regression potential of a bug-fixing commit is that the bug is more likely to be a regression bug if the code relevant to the bug is changed frequently in the history. Consider the example, the buggy code A has been changed by many times in the history, which makes it more likely to contain at least one change, making an existing function fail, thus causing a regression bug. In contrast, the buggy code B has much less regression potential comparing to A. In this regard, we can have a rough estimation with this equation. Here, P represents an empirical bug-introducing probability, N represents the number of changes, and a set represents the set of relevant buggy code. In our work, we further refine the formula to improve its flexibility. The interested audience can refer to our papers for more details. Next, we introduce how we migrate the test case and its dependencies. Given the time limit, we can only provide a brief illustration here. More technical details are available in our paper. Given a test case in a bug fixing commit, we first extract all its relevant code in the commit. Next, we isolate the code elements where the fix happens. Then, we further extract the static and dynamic dependency of the test. Here, the green code elements are the elements depended by the test case. By comparing the difference, by calculating the difference between the bug fixing commit and the to be migrated commit, we can know what dependency should and should not be migrated. For example, the element where the fix happens should not be migrated. Also, we will not migrate the dependencies which have already existed in the to be migrated commit, which is highlighted in red here. Finally, we migrate all the necessary code elements, all the necessary dependent code elements. We also define rules to reconcile the migrated code regarding the compatibility of the library versions of two commits. In order to search for a commit where the test case can further pass in the history, a straightforward method is to use git bisect solution. The solution assumes that each commit in history can either pass or fail the test case. Also, it assumes that the passing and the failing commits are generally consecutive. If a commit failed the test case, we can just move forward. And if the commit passes test cases, if the commits pass the test cases, we can move backward. A binary search strategy can be applied in this case. However, in practice, some commit cannot compile. In addition, the test migration might not be successful in some other commits. It means that the binary search strategy can stuck on some commits without the feedback to move forward and backward. Our rationale is to enhance the binary search by efficiently identify a non-feedback region. By this means, we can soon escape from the region to further the binary search, and the audience can refer to our papers for more details. Based on our approach, we build our tool, RegMiner, which can show the progress of mining regression bugs and visualize the details of how we search the commits and migrate the test cases. Once a regression is mined, we can further allow the user to investigate the regression-fixing commit and the regression-introducing commit by visualizing the code difference and running the test case against the commits and observe the outcome in the console. We evaluate our approach with 3 experiments: a closed word experiment to evaluate whether RegMiner can accurately and completely mine regressions from Git repositories, an open word experiment to evaluate whether RegMiner can continuously mine authentic regressions from real-world Git repositories, and an ablation study to evaluate how does each technical component in RegMiner contribute to the mining effectiveness and efficiency. In the closed word experiment, we manually provide 50 regression bugs and 50 non-regression bugs. We investigate whether RegMiner can report regression bugs while ignoring those non-regression bugs. Given it is an information retrieval problem, we use precision and recall as a metrics. The results show that we can achieve the precision of 100% and recall of 56%. The main reason for the low recall lies in our limited engineering support and test migration. We observe that the projects can be very diversified. For example, some Maven projects require complete license information in the code so that they can have a successful compilation. In addition, our predefined rule to reconcile the migrated code may not be applied in some cases. In the open world experiment, we run RegMiner on a set of collected Git repositories for 8 weeks. RegMiner reported 1,035 regression bugs from 147 projects. We manually evaluate 90 reported regressions, and it shows that there's 1 false positive. Our investigation on this false positive shows that the reference test case can sometimes accidentally pass the previous version, while the feature has not been implemented yet. In this work, We assume that the relevant features in the bug fixing commits can exist in the to be migrated commit if their test coverages are similar. And for these feature existing problems in the code evolution history, we will investigate a more reliable technique in our future work. Finally, our ablation study generally showed effectiveness of our technical solutions such as regression fixing commit prediction, test case migration, and a search strategy. We compare our RegMiner with various options and showing that our approach has the best performance in the study. In this work, we introduced RegMiner, a solution to fully automate the regression bug collection, which requires minimum human interventions to construct a regression bug dataset. We propose various technical solutions to overcome the technical challenges. While our approach is effective in general, RegMiner still suffers from the limitation of low recall. In the future work, we will strengthen the tool with some more engineering efforts. For example, we will further design on-the-fly library downgrading technique to minimize the compilation errors during the test case migration. Thanks for your time, and we're happy to address any questions.